Welcome to lecture number 12. And so far we have been discussing about one of the major themes of this course, that is the structure property correlation. You must be wondering why we are talking so much about that. Well, if you want to do machine learning based modeling on materials design and discovery, first you should know what are the target properties or target set of processing conditions to be adopted. That is why I am giving you an overview of the different kinds of materials, their properties, and now today onwards we will talk about processing of the materials. Obviously, I cannot do justice to the whole thing, because this itself will consist of several courses, but what we are trying to do in this case is basically to give you some perspectives, so that you can use this knowledge for modeling using machine learning or deep learning. So, let us talk about the things there. First, as usual, we will do some recap what we have learned in the last lecture, and then we will go ahead. So, as I told you in the last so many lectures, maybe 5 to 6 lectures or so, we have been talking about this basic theme, that the basics of material science engineering depends on the correlation between processing, structure, properties. So, how the structure will control the material properties, we have discussed about it. Now, we are going to talk about how processing can be made, processing steps can be used to make or prepare certain kind of materials. And we talked about all kinds of properties, obviously not everything possible. We talked about mechanical properties, then discussed about electrical, electronic properties, and some part of magnetic properties. Well, as far as the electrical property is concerned, we discussed about conductors, semiconductors, insulators. In this picture, you can clearly see that for any electrical transmission, you need combinations of these materials. How do you characterize them? What are different parameters used to characterize this kind of materials like conductors, semiconductor, insulators? What are the basic theories of understanding the behavior of these kind of materials? We have talked about it. And most important thing about semiconductor is that they are used in our daily life, that is for making various kinds of electronic devices, whether it is a computer, laptops, or mobile phones, or anything else, and there you need to use this kind of materials to make devices. And then we talked about little bit about the models available to understand the electrical properties or electronic property, like Drude model, which is classical model, and then some quantum mechanical model like conic-penny model, as well as we talked about little bit about band diagrams, which can explain the conduction of electrons from valence band to conduction band. And finally, I talked about magnetic properties in the last lecture, and because magnets are used widespread used in the application in the real world, and what are the kinds of magnets we need to use, what are the properties we look for. So, design of magnetic materials will be important when you use machine learning. And magnets are omnipresent, as you can see, and naturally magnets are available in the bacteria. Actually, there are magnetotactic bacteria which contains chain of magnetic crystals of very fine scale crystals of 35 to 120 nanometers in diameters, and they are capable of generating magnetic field, which is enough to align these bacteria with respect to the earth magnetic field. You have to understand earth magnetic field is very weak, still these bacteria are able to navigate using the earth magnetic field or interaction of earth magnetic field with these very small magnets. So, these are some of the pictures of the magnet on the right side. You can see here they are nanometers, and we know 1 nanometer is 10⁻⁹ is -9 meter. So, that means each of these magnets is basically very small, and they align themselves in a particular way, so that they can provide you strong magnetic interactions with the earth magnetic field. Well, magnetic materials are basically characterized by magnetization, and when you apply field, we can actually create magnetic. When you apply when you start passing electric current through a coil, you generate magnetic field. Okay, that is what is shown in this picture on the left side. As you can see, that electric current is passed through this coil, and because of that magnetic fluxes or lines of forces are created, and then finally, once you test this magnetization ability of a material as a function of temperature, you see the magnetization decreases as a function of temperature, and beyond a certain temperature magnetization becomes 0. That is what is known as a Curie's temperature, or many people call it Curie-Weiss temperature. That is a TC. There are many magnetic materials available in the world. Most important are the transition metals like iron, nickel, cobalt, or oxides of them like iron oxide. Fe3O4 is a very well known magnetic material which is called magnetite. And for the magnets, most important property is this magnetization, magnetization versus magnetic field, what is called hysteresis loop or MH loop. Some people call also BH loop. BH stands for the magnetization and H stands for the magnetic field. So, if I take magnetic material, apply field, what will happen? The magnetic strength or magnetization of the material is basically can be obtained from this kind of diagrams. Here several parameters are important. First is the important parameter is the remnant magnetism, and the magnetism remains in the material when the magnetic field goes to 0. And then you have a coercivity. When you have when your magnetic field, coercivity is what is the field required to remove the magnetization. That is what is called coercivity. And then the last thing is the saturation magnetization, which is corresponding to point B here. So, these are the parameters which will be used for as a feature when you use a machine learning model. That is what we are trying to convince you. And magnetic material is basically what is the reason for magnetism is basically electron spins. As you can see here, this is nucleus and the 2 electrons are rotating. If the spins are opposite, there will be no net magnetic moment. Therefore, it will not show any magnetization. But if the spins are resultant spin is either in positive or negative, that is the case here. You can see here one of the electron has a negative spin, then it will lead to magnetization. But if you have all the electrons, does not matter how many electrons are there, if their net magnetic moment or net spins is 0, then there is no magnetic moment. But all in case of transition metals, they are d band field, therefore what happened? There will be the d bands, many times the electrons are aligned only in certain direction, like in case of iron, there are 3D transition states of electrons have perpendicularly up electron spin, and that gives you the magnetization. Exactly same thing what we talked about in the last this case also. The moment you pass current through a coil, it generates magnetic field. Same thing happen. Electrons has actually charge, and when the charges are actually aligned in a particular direction, it provides the magnetic field or magnetic moment. And now question is, depending on the type of magnetic moments, you can have paramagnetic, antiferromagnetic, ferromagnetic and ferrimagnetic materials. And in case of paramagnetic material, spins are random. So, therefore, there is no resulting magnetic moment. In case of ferromagnetic material, spins are perfectly aligned to in a particular direction, as you can see for this figure C, and therefore, you have a strong magnetic moment available for the material. In case of ferrimagnetic material, there are opposite spins where values or magnitude of the spins are not same. So, therefore, there is a resulting magnetic moment. Obviously, magnetic moment for D is much lower than magnetic moment for the C, right, because of the problem of this negative and positive cancellation, whatever remnant or remaining is providing you the magnetic moments. And for the antiferromagnetic material, you can see that spins are opposite to each other, right. You can see on a one row of this, let us consider this or you consider this, they are cancelling each other. So, therefore, there is no permanent or magnetic moment available for these materials. This is how we can explain why magnetization is developed in the material. And as you know, that is talking about spins, right, but in a particular grain, as we talked about it, you can have many thousands of electron presence, right, for a material. Now, the spins, depending on alignment of the spins, you can have domains actually, and these domains will be separated by domain wall. As you can see here, this is all taken from the Michael Aspie's books on nanomaterials and nanotechnologies. The spins can be aligned in a particular way, and then there will be switching over of the spins possible from one domain to other domain, and that is how we can actually explain the domain formation in a magnetic material and how these domains can basically lead to magnetization. And last thing I talked about is if you have small particle size like nanomaterials, what will happen to the magnetization, right. As you see, the plot shows the behavior above a certain grain size or particle size, whatever you call. Grain size is a better terminology. The magnetic moment remain same, or the coercivity here is plotted AC. The coercivity remains constant, but below certain values of the grain size, coercivity start increasing rapidly. That is why actually each of the grains become a single domain. There is no domain wall then. When the grain size is bigger, you can have domain walls within the grain, and these domain walls, as you know, between the two domains there is a switching over the spin, and domain walls can reduce the magnetic coercivity. But if a grain becomes single magnetic domain, then its AC or coercivity increases very rapidly. That is what you see here. But if you still decrease the grain size, thermal effect comes into picture. The 3/2 kT factor, K stands for the Boltzmann constant, T stands for the absolute temperature. That factor can alter the spins actually, when the grain size become very small. That is what is called SP, or that is called the basically super paramagnetism. Then AC becomes very low, and that is why the paramagnetism start developing, spins become random, you do not see any magnetization. So, this picture, the left side shows everything: saturation, remnant magnetization, coercivity, and also some flux density, right. So, these are the parameters which we will be using for these aspects. Let us now talk about, that was the recap, let us now talk about processing, right. So, what do you do when you process material? You alter the material shape, right. You alter physical properties, or you alter sometime appearance in order to add value to this particular product, right. Very simple. This is a pen which is used to write on the computer screen. So, therefore, when it is made a particular shape, and also it is made with certain important property requirements, and its shape is exactly like a pen, right, with the way you write. So, therefore, when you manufacture something, your basic objective is to produce a particular shape of material with certain physical properties, and also it should be looking good, then only you will purchase it, right. So, that basically three categories of processing operations. First one is called shaping operations. In that operation, you alter the geometry of the starting work material, right. That is what you do. And then you have also second operation is known as the processing enhancing operation. It improves the physical properties or even some of the chemical properties also without changing the shape. Okay. That is a classical example is the heat treatment. In material science engineering, many times you heat treat a material. There, do you change shapes? Answer is no. We do not change any shape, anything, we simply heat and cool, and in that process you enhance the properties, right. You enhance the strength of the material, you enhance sometimes conductivity of the material. So, therefore, that is called property enhancing operation. And then third one, which is very important nowadays, is called surface processing operations, in which you can clean, you can treat, you can coat, or you can deposit materials on the exterior surfaces of the work. That is very widely used nowadays. Okay. Think about the walls of the house, you always paint it, right, in order to protect it from getting degraded by the environmental aspect, sunlight, dust or moisture, whatever it is. Okay. So, the surface processing operations are very critical nowadays. So, hope you understand the three categories of processing operation used for any kind of manufacturing. Now, how do you shape? Because shaping is what is most important in material science, right. You can shape in many ways. First, you can do solidification processing, like you can start the material in liquid form or semi fluid form, and then put it inside a mold of particular shape, and it will take, like if I take water, whatever I will put the water, it will take the shape of that object, right. Same thing will happen for the liquids of any material, like if we can produce. So, solidification processing is widely used for metallic materials. It is not so much used for ceramics, some cases it is used, but widely used for metallic materials. That is why it is produced to prepare any kind of small, large, big, extremely extra large, extra big kind of objects. Then second important process is the particulate processing material. Okay, let us think of incandescent bulbs. I given you example, right. The bulbs in which we have a coil, tungsten coil, right. So, tungsten has a very high melting temperature, something about 3400 degrees Celsius temperature. You cannot melt it easily. If you want to melt it, it will require a furnace which can go up to 3500 degrees Celsius temperature. It is not possible to have such a kind of furnace like that, right. So, what do? You start producing tungsten powder, and then using this powder you can produce tungsten coil. So, there are many such objects are produced from that. How many of you know that on the missiles some of the fins are made of pure tungsten? These materials are made of tungsten. Why? Because they can withstand high temperature. When a missile moves at a very high speed, interaction of the missile with the air, or the rather friction with the air, can generate a lot of heat, and it can melt even many things in the world. So, we have choice of using tungsten only, but then we have to make a solid tungsten. How do you make it? How do you give the shape of the fins? Okay, is using by powder processing of the material. That is what is called powder metallurgy in many cases, what is called PM or powder metallurgy. Now, third important shaping operation is called deformation processes. So, we can start with the ductile material, relatively ductile material, and commonly metal or metallic or alloys, and then you deform it to give a shape. Okay. Classical example is the connecting rod, which is used in the engine. In a car engine you have a connecting rod attached to the engine. It is processed by deformation processing. Many such things are produced. Wheels of the railway are produced by the deformation processing. So, this is also very important. There are many deformation processing exist in the world: rolling, forging, extrusion, sheet metal forming, and many others are there, right. And fourth one, which is called machining, in which you remove the material. It does not matter if the material is ductile or brittle, you can machine it out, right. That is very simple. So, these are the 4 different shaping operations you should remember, and you can shape them. So, therefore, when you select, suppose in machine learning they ask you to provide what will be the best processing route to make a particular material, a particular component rather, you must know which one can do what. That is why we are talking about the shaping operations. So, here I show you everything in one snapshot. The first one is a casting, in which you start with the liquid metal, pour inside a cavity of that particular shape and get it. In powder processing, you start with the powder, put it between two inside a die with punches. You have a cavity, that is called die, this cavity, and the punches apply forces or temperature both to make them centered or to make them compact, right. You can also go for deformation processing. This is shown as a forging. You have 2 dies, you can see of particular shape, put this hot material inside this die and apply forces or strain, whatever, deform this, correct. Or you can have extrusion, you can actually force the material to pass through a die with a certain orifice or hole, and then it can give you the particular shape. You can see all the pipes, many of the pipes in the world are made by these extrusion routes. Your toothpaste tube is basically made by extrusion processes. And machining, obviously everybody probably has seen, if you are engineering, from engineering background, you know the machining is a major industry in the world to produce different kinds of objects. Well, that is about it. Now, most, as I told you, oldest and the widely used technique for shaping operation is what? Basically the solidification processing, like casting or plastic molding. Okay. You could see these 2 pictures, how it is done. If the liquid metal is poured inside a sprue or cavity, then it is passed through certain certain pipes, and finally it reaches this cavity and fill it up. Once it completely filled up, you allow it to solidify. Okay, this is the sand mold, that is how this cavity is prepared, and once it is completely solidified, you take it out, you remove this part, this extra part, okay, and then get your casting available to you. Well, this is very old technique, very old. It is almost as old as civilization, right. You must have seen this picture on the left side, the dancing girl of Mohenjo-daro. It is almost 4,000 to 5,000 years old, and we also know this mask of Tutankhamun from Egypt. Okay. This is also almost 4,000 to 5,000 years. Remember, this is pure gold. So, in those time, the human or the people knew how to shape gold actually, and this one is a statue which is made by casting. Okay, Nataraja statue is almost about 1000 years old. So, you can find lot of things in Wikipedia and search it and find out different kinds of the statues made up of this casting operation or cast structures. Well, not only that, many of machines, actually machining things are made by castings. Let us talk about a car engine. This is a car engine, 4-cylinder car engine. You can see there are 4 cylinders. This is a single cast product. It can be either made up of cast iron or it can be made of aluminum silicon alloy. Nowadays, many of the car engines are made of aluminum silicon alloys. This is a brake drum, okay, used for braking operation, brake. This is a compressor housing. This is gear housing. These are all cast products, and this is engine block. So, these are very common. So, lot of these products are made by using this technology of casting. Okay. You can clearly see how complicated the object is, but still it can be made by casting routes. Well, how it is done? Well, this is very simple. These pictures are taken in the IIT Kanpur, the engineering metallurgy lab. So, first you have to melt, first you have to make a liquid, right. So, that means melting, take the solid pieces, melt it down in a furnace. After it is melted, you can see after melted the liquid is taken in a container, okay, that is called basically ladle or something. Then it is poured inside these molds, okay, you can see that it is poured here, and once it is completely filled up, then it is allowed to solidify. After solidifying, you can get this kind of casting easily. That is in a layman's point of view, this is what is the process is, but scientifically the process is much more complex. You have to understand that very critically. So, there are a lot of fundamental factors. Solidification of any material from molten state is not simply taking the heat from the liquid and allow it to solidify. There are many aspects are there. First is heat transfer, obviously. You have to take the heat away during solidification or cooling of the material in the mold. How you can take the heat away, what are the best way of taking the heat away, whether fast is good or slow is good. And then you have fluid flow. You are pouring a liquid is going through the different channels. The flow of the liquid inside the channel is very important, or in the mold cavity rather. So, there will be a lot of influence of the mold material in affecting both the heat transfer and the fluid flow. So, whether you use sand, whether you use something else, that will affect these kind of aspects. So, I am not going to talk about details about that, because how these are actually going to play a role, because this itself is a subject which you can find out courses on NPTEL. So, but you do not need to know such a detail all these aspects, you must have some idea, because if you want to model it, you should know what are the factors which control the solidification behavior, and what are the factors which can be important to be considered. Many cases you need to get the data of those, because machine learning or deep learning is basically data in database or data related engineering. So, therefore, what kind of data are required, where from we will get this data, and how to process the data, that is what something you should know. And that is why before talking about those aspects of machine learning, I am giving you some perspectives of this. So, let us stop it here for the part 1 of the lecture. So, we will talk about part 2 and talk about what are these factors and what are the different solidification processing can be adopted. Thank you.